Hi, Jeffrey. Thanks again for coming to Stats 385 Theories of Deep Learning. So as my first question, can you tell us about yourself and your current work in Google?
Yeah, absolutely. So a little bit about my history. I guess my educational background is in theoretical particle physics. Did my PhD actually here at Stanford. Spent a lot of my time up at the Stanford Linear Accelerator Center, SLAC. During the course of my PhD, I realized that maybe academic physics wasn't necessarily where I wanted to go, and I got involved with some of the goings-on here on campus in terms of machine learning, got interested in deep learning, and spent a good portion of my PhD pursuing some of those ideas, sort of on the side, and eventually decided I wanted to pursue a postdoc in natural language processing, which I did here at Stanford with Chris Manning. After that, I joined Google. I am now a research scientist there on the brain team. And recently I've been doing a lot of work on trying to understand the theoretical properties of neural networks, using a variety of techniques inspired to some extent or another by my background in physics. Recently I've been using some tools from random matrix theory, generally trying to just understand how it is that deep learning works, and I think that's a question we're all interested in.
Okay, great. So in this course, we have had several guest lectures prior to your lecture, and so they took different views to deep learning theory. For example, we had people that took the view of harmonic analysis to study deep learning, or approximation theory, or Zaid Harchawi looked at it from the perspective of reproducing kernel Hilbert spaces. So you are using a different technique, which is like random matrix theory. So what do you think random matrix theory can offer to deep learning?
Yeah, I think that's a great question, and I don't have a full answer for you. I think the door is wide open at the moment. I think some of the motivation for studying random matrix theory in the context of deep learning comes basically from the analysis of large complex systems. So if you take the analogy of thermodynamics, for example, it doesn't really make much practical sense to try to study the dynamics of every underlying degree of freedom, to try to specify the position and momenta of every particle in the air in the room. Even if you could do so accurately, it wouldn't really give you very much predictive power. And I think in the context of deep learning, trying to get an exact theory where you know, say, the learning dynamics of every parameter in your model and how it corresponds to generalization, et cetera, is really an unachievable goal. Even if you did achieve it, you wouldn't really get very much practical benefit out of doing so. And at least in the context of some physical systems, considering higher level kind of bulk variables, not the underlying degrees of freedom, but things like the temperature and the pressure, describe the system as a whole and give you much more insight into sort of the practically relevant aspects of these large complex systems that maybe you care about. And as far as neural networks go, I think if we approximate the parameters, the underlying degrees of freedom with random variables, we can draw similarly high-level concepts that are maybe useful in building up a mathematical formalism and some insights into sort of the bulk behavior of these systems. And so that's kind of where the random variables aspect comes into play. And the matrices part, of course, is just because in neural networks, everything is a matrix. And you know, from Jacobian matrices to Hessians, what we care about are things that are intimately related to the matrix structure itself, like the eigenvalues and eigenvectors. And so the matrix structure is relevant, and I think the random variable perspective is useful for building up high-level conceptual insights into the theory. And so for these reasons, I think random matrix theory is highly appropriate in trying to build up a better theory of deep learning.
So can you give an example of, I know you're going to talk about this in your lecture, but what do you think would be surprising for practitioners from a random matrix theory perspective? Like you have 3 papers that you introduced for this class to study. And so can you just briefly tell us what would be a surprising fact?
We do have some surprising results. I think the most surprising of which is regards the sort of the conditioning or trainability of very, very deep feed-forward networks. And in particular, we find that ReLU networks that are very deep actually train much worse than sigmoidal networks of the same depth. I think this is counter to a lot of the intuition people have built up, suggesting that ReLUs are solving the vanishing gradient problem, for example. And it seems like our analysis suggests, at least in the very deep case, hundreds of layers maybe or more, that actually this is not the case.
And we have this tradition that we give you a topic and you give us up to 3 words about them. So, S transform.
Multiplication of spectra. 3 words, it's hard.
Still-just transform.
Moment generating function.
Surya Ganguly.
Jovial physicist.
Dropout.
Overhyped for generalization.
Glove.
Word embeddings.
Stanford University.
Alma mater.
Great. So I'm going to pass it on. Thank you so much.
So this is a course on theories of deep learning, and as I'm sure you know intimately, deep learning is largely an empirical subject. And many of the practitioners don't have a great deal of insight into the theoretical culture. So I thought we could just discuss for a moment some of the ways that random matrix theory has interacted with the real world before. So there's a famous event in the 1950s called Wigner's surmise, where Eugene Wigner looked at the properties of eigenvalues of random Hermitian matrices and suspected that those had something to do with the energy states of atoms, and then launched a whole tradition in mathematical physics following up on that. And then 15 years later, there was sort of an amazing seminar at the Institute for Advanced Study where there was a presentation of properties of an important number theoretic function, the Riemann zeta function, at which it became clear that there were parallels between the zeros of the zeta function and, again, eigenvalues of random matrices. And a number of important conjectures came out of that. So theorists in physics are aware of these important but not completely conclusive and somewhat speculative connections, and are very inspired by these key moments in intellectual history. I'm wondering, have these been inspirational for you? And if so, why? If not, why not?
That's a really interesting question. I think my answer may take a turn that you're not expecting. In fact, some of this work was inspiring to me not really from the historical context, but really from the methodological context. My work in graduate school focused heavily on developing calculational methods in perturbative quantum field theory, which relies heavily on some diagrammatic tools called Feynman diagrams, which are convenient ways of basically representing graphical objects and encoding certain types of computations relevant for high energy physics. And this type of diagrammatic analysis was sort of the bread and butter of a lot of what I was doing in my PhD. And when I started thinking about deep learning and random matrices in that context, especially with regard to the moment method in random matrix theory, it dawned on me that a lot of the underlying tools and techniques that I had been using in my PhD are actually very similar to some of the tools that are used in these methods of proof, especially the moment method. And so I felt quite at home because of that. And I think it's quite interesting that some of these techniques in random matrix theory originated from this physics vantage point, specifically because the method of analysis was based in these sort of Feynman diagrammatic tools. That's a sort of long-winded way of getting at one aspect of your question, not the historical one, but that is how I connect to the field, yeah.
So practitioners probably also feel in looking at the question of bringing theoretical models from random matrix theory into play that the matrices involved are very specific. For example, you could have Gaussian independent identically distributed matrices present, whereas a trained deep net has some concrete numerical properties that might not seem to be very much like purely random numbers from a random number generator. I mean, in some ways they might be similar, but it might seem that there are some differences. So another inspirational thing has been a lot of research over the years has found that properties that were once found for random matrices in very specific models turn out to be quite generic. And so there are universality hypotheses that have been encountered again and again in high-dimensional analysis that again and again show that if you do the calculation using some very simple physics-inspired models, you get an answer that's correct with surprising generality. And I'm wondering what role has this style of thinking played in your analysis and your approach?
Yeah, absolutely. I think this concept of universality is somewhat critical for the success of the type of analysis that I've been thinking about. The way that I've interacted with it is sort of more from an empirical standpoint. One could obtain matrices derived from trained neural networks, look at Jacobians, Hessians, activation matrices, and whatnot, look at their spectra, and lo and behold, it looks like the spectrum that you would derive from a Gaussian random matrix. Maybe that's a slight generalization of the types of behavior we observe, but at the moment we don't have a great understanding for how this universality might emerge. But empirically it does seem, to an extent that's quite surprising to me, that indeed it does hold. So I think this is an avenue that's ripe for future research, trying to understand the extent to which these universality principles apply in deep learning. But as a first level of approximation, it does seem that making some simple underlying random matrix distribution assumptions seems to be a pretty good one.
So there are many, many different deep nets that have been proposed. I think probably another 1,000 will be proposed this year at NIPS, which is happening in a few weeks. which of those models seem to be most appropriate for the point of view that you're promoting in your talk today?
That's an interesting question. I think I'll be promoting several points of view, but the one that's maybe most relevant to your question is the point of view that it's possible to train very, very deep feed-forward networks with the right initialization and using sigmoidal and not rectified linear units. And from that perspective, I think some of the recent models that might be interesting to re-examine with this framework would be, some of these ResNet models with hundreds or thousands of layers, or recurrent neural networks that span long time horizons, with capable of doing so with like LSTMs. Basically, models that effectively generate hundreds of hidden layers or thousands. And in that context, I think a very interesting question is, to what extent are the architectural choices, such as the residual connections, batch normalization, the gates in the LSTM, to what extent are those giving a good inductive bias for solving the problem, and to what extent are they simply making training feasible? And I think we might be able to shed some light on questions of that type using some of the techniques that I'm advocating.
So as a final question, when you speak to your Google colleagues about work in random matrix theory, do you feel you have to sort of prepare the battlefield and lay the grounds for discussion so that they'll be open to this? Is it something that you consider challenging among computer scientists and people with a more traditional deep learning background? And so how do you deal with your position as a theorist in that context?
I think it's nothing specific about random matrix theory, but generally trying to develop theory for deep learning, one typically is a few steps behind practice. That's just the name of the game. And it's always a struggle to try to make predictions that can be actually informative of new model developments and whatnot. And the extent to which you can make such predictions, people are extremely eager to hear about them and try them out. And I think that's just sort of the nature of this exploratory field. People, I think generally speaking, not just at Google, but across the board, who are practitioners, have less interest in understanding why something works if they already know that it does work, except insofar as that knowledge might help them build new and better models. So broadly speaking, people are very receptive to new insights if it might help them develop some new cool model. And I think that's just the life you choose if you're a theorist.
Thank you.
My first question is, if you had all the resources of Google at your disposal for 24 hours, how would you use them in order to advance theories of deep learning?
That's an interesting question. I guess first I should just say for the record that my opinion on this topic is not one of Google.
Can we edit this?
Just my personal opinion. What I would like to do might be a large type of architecture search, where I could deploy resources to try to find new and interesting optimization algorithms and network configurations. I think this is a very promising way forward to advance our understanding and our tools in deep learning, but it's a very computationally expensive one. So yes, if I had lots of resources, I might pursue these directions.
And how would that advance theories of deep learning? You're hoping to stumble upon an architecture that might be more explainable, perhaps?
I don't know if explainable is what I'm after, but if there's a kind of smoking gun for a type of architecture that works really well, or an optimization algorithm that just stands out way from the crowd, then that gives you a strong signal that there's something there which we need to understand. And right now, I think the situation is we have a whole host of things which are working fairly well, maybe some a little better than others, but we don't have a strong standout pointing, here's where the key lies to how deep learning works.
How would you go about doing that? Specifics, if you can. Maybe I can ask like a better question. So, would you, for instance, just change different nonlinearities, or going to your work, would you, for instance, do a grid search over different initialization standard STDs?
I think one of the more promising directions would be
Standard deviation.
Would be more like reinforcement learning approach, and with a huge amount of resources, you can sort of make parameterizable a huge number of components of the network, including all kinds of connectivity issues, activation functions, pre-processing steps, et cetera, et cetera, et cetera. And if one were to explore the full range of those possibilities using more of a reinforcement learning approach, where a lot of these things aren't differentiable choices, I think it might really reveal some interesting stuff.
Okay. For the second question, if you could plot the happiest outcome of theories of deep learning, how would the image look like?
The happiest.
Imagine you're like a producer in a movie, and it has to be a happy ending.
Well, this is a bit a risky topic, I guess, but I think it's conceivable that we could really stumble upon some concepts that are relevant for some notion of intelligence. And I think lots of people would be very happy if we could understand that to some extent.
Jeffrey, thank you again for coming to Stats 385, and we look forward to your lecture.
It's
Thanks.
my pleasure.
Okay, let's get started. Thanks again for coming to Stats 385. Today our guest speaker is Jeffrey Pennington. He is from Google, New York. He's a research scientist at Google. Jeffrey has done his PhD here at Stanford and worked as a postdoc for 2 years with Chris Monning, where he developed GLAV, which is a very popular word embedding method in NLP. Today, he's going to talk about a random matrix theory and how it applies to deep learning. Jeffrey, please take it away.
All right, thank you. Yeah, it's really great to be back here at Stanford. Today I'm going to be telling you about some of the things I've been working on over the past year or so in relation to trying to build a better mathematical formalism and framework with which to try to understand deep learning. And I'll try to convince you that random matrix theory should be an important ingredient in such a formalism. So just to give you a brief outline of what I will talk about today. So first I'll try to give some high-level motivations for why I think random matrix theory is particularly pertinent to the study of deep learning. And then I'll just highlight a few essentials from random matrix theory that I'm going to be using to describe some of the recent work I've done in this direction. And I'll first try to talk about the geometry of high-dimensional loss surfaces. Then I'll talk about training very, very deep neural networks using sigmoidal units instead of rectified linear units. And if I have time, I might try to touch on some recent work on nonlinear random matrix theory. So just to begin, why should we be thinking about random matrices in the context of deep learning? So I think the first and probably best reason for this is, of course, that at least for every optimization procedure I know that's used in practice and every weight initialization scheme that seems to be successful, the initial weights of a deep neural network are taken to be random variables. and their random matrices. So this is the first and primary reason why we might want to study random matrix theory in this context. Of course, one point that is often brought up in this context is during the course of learning, weight updates are made which induce correlations between the weights. So why would you expect random matrix configuration to be a good description beyond the initial point in learning? And I think that's a very valid concern and is particularly relevant for small models where the number of parameters is relatively small compared to the number of samples, the number of training examples. And in that case, I do think that it's very likely that you induce correlations that break some of the random matrix assumptions. But in deep learning, the configurations that seem to work well in practice are in the opposite regime. They're in the highly over-parameterized regime, where you have many more parameters than you have samples. And in that case, I think, although I don't have concrete proof of this at all at the moment, so it's somewhat of a conjecture, but I think that training induces only low-rank perturbations around the initial random weight configuration. So you can imagine one limit of this statement, which I think should be fairly obvious and intuitive. Suppose you have 100 billion parameter network, and you have one training example. Even if you train your loss function to 0 loss, the correlations induced in this 100 billion dimensional space by that one training example are very likely to be low rank. And so just carrying that analogy forward a little bit, I think it's quite likely that if you're in the over-parameterized regime, a random matrix assumption on the weights, even after training, may end up being a very good first approximation. So this is the first motivating factor. Slightly more abstractly, I think that in our efforts to try to build an exact theory of deep learning, I think it's likely to be totally intractable and probably uninformative. And by exact, I mean some description of the learning dynamics of every parameter in the network, with some information about generalization, performance, etc., depending on those many, many parameters. I think a good analogy for this comes from the study of complex systems in physical sciences, for example, statistical physics or thermodynamics, where if you want to discuss some properties about, say, the air in the room, one option would be to try to use Newtonian dynamics and describe the position and momentum of every single molecule in the air in the room, and from that derive things you care about. That's sort of like the first principled approach. But we know that it's much more useful to describe certain quantities about the room as sort of high-level abstractions, like pressure and temperature. And in terms of these high-level quantities really are a lot more intuitive, and they're more robust in making actionable predictions. So I think in deep learning, we're in a similar situation where we don't want to be talking about exact solutions for the learning dynamics of every parameter. We want to come up with the analogy of temperature or the analogy of pressure, something like this, as applied to deep learning. So these are two examples of why we should care about random variables in the context of deep learning. Why should we care about matrices, random matrices specifically? And I think to answer this question, the answer is quite simple, I think, because many of the important quantities related to optimization and learning are critically related to the matrix structure of, for example, the Hessian matrix. The matrix of second derivatives tells you about the curvature of the loss function. And so the quantities which are derived from these matrix properties are of particular relevance. And so it seems pretty natural, I think, to consider random matrices in the context of deep learning. So just to dig a little bit farther into this matrix aspect, which matrices do we typically care about? I mean, in deep learning, there's lots of matrices that crop up. For example, the post-nonlinearity activation activation matrix, which I'll call Y. Here I've written down the layer-to-layer recursion relation between the activations at layer L-1 and the activations at layer L, some nonlinear function f. And this matrix has two indices, the I index corresponding to which neuron we're talking about, and the mu index indexing which example we're talking about. So we have a neuron by example activation matrix. This is sort of the crucial, the workhorse in a neural network. It tells you how information propagates through the system. And okay, another matrix which is obviously relevant for optimization, which I mentioned previously, are the Hessian matrices, the second derivative of the loss function with respect to the parameters. If you have a L-layer network, the Hessian is L by L block matrix. And it turns out that at least for squared loss, the bottom right-hand corner of this matrix is exactly Y transpose. So we see again the activation matrix appearing now in the context of the Hessian, which I'll, if I have time, come back to that point. And another matrix that I'll discuss today are another set of matrices are the Jacobian matrices, derivatives of the output of the network YL with respect to the input Z1. So this is the input-output Jacobian matrix. And if you just follow through the recursion relation in the first line with the chain rule, you can write this matrix as a product W times D times W times D, where W are the weights and D are diagonal matrices whose elements are the derivatives of the activation functions. Okay, so these are just three examples of matrices that are relevant in the context of neural networks and deep learning, and I'm going to talk about some of them going forward. But basically, this is all I wanted to say about why I think it's important for us to consider random matrix theory as it applies to deep learning. Okay, so having said that by way of motivation, I will now say a few things about some of the underlying mathematical tools that I'll be using from random matrix theory. And when I say essentials, I don't mean mathematical essentials as in sort of the pillars of the mathematical construction of the field. I really just mean some of the tools. And so just to give the basic building blocks of the tooling that I'm going to be using. And to do that is actually not so challenging. And hopefully I can do that in just a few slides. So the main object that I will be concerned with is basically the set of eigenvalues of a matrix, a random matrix M, whose entries may be random variables. And for this matrix, the empirical spectral density just is the average of delta function densities located at the location of the eigenvalues. So this is just a fancy way of talking about the set of eigenvalues of a finite dimensional matrix. And you can think about this kind of in terms of a histogram, where each bin is telling you the likelihood of finding an eigenvalue in that range. For the most part, considering random matrices of finite dimension is technically much more challenging. And so for most purposes in this talk, I'll be considering the limit where the matrix dimension actually goes to infinity. So this would correspond in many ways to having an infinite number of parameters, or having a layer in the neural network of infinite width. And in many cases, I think these are good approximations. But finite width corrections would be an interesting topic to investigate in future work. But in this limit, as n goes to infinity, if you have a sequence of matrices of increasing size, then the limiting spectral density is just the limit of rho sub n. And so here, if the limit exists, it might look something like this. So the primary object that we're going to be talking about is this spectral density. It's a continuous limit of the density of eigenvalues, and it's going to be sort of the workhorse. And from it, we'll be able to derive pretty interesting things related to learning dynamics in deep neural networks, etc. So given the spectral density, there are a number of related quantities that are particularly useful for our analysis. The most important of which is known as the Stieltjes transform. So the Stieltjes transform is just an integral of the spectral density. And it's a function of some complex variable z. But if you have the density, you can just do this integral and obtain the Stieltjes transform. And in the next couple slides, I'll highlight the ways in which this is particularly useful in the study of random matrices. But one of the reasons why it's nice from a theoretical perspective is that it encodes in its imaginary part the spectral density itself. So let me just explain that in a little bit more detail. So in the first line here, I've just used a trivial identity to rewrite the spectral density as an integral of the spectral density against a delta function kernel. So this is just a trivial rewriting of the density. And then I'm going to use a representation of the Dirac delta function in terms of a limit of a Poisson kernel. So if you look at this expression for delta x in the middle here, if x is 0 and you take epsilon to 0, then you get infinity. If x is non-zero and you take epsilon to 0, you get 0. So this is the kind of definition of the Dirac delta function. Then you can just do a little bit of rearranging and write the delta function as the imaginary part of 1 over x plus I epsilon. So then you can take this representation for the delta function, plug it into our expression for rho, and recognize that what results is exactly this expression for the Stieltjes transform G. Which means that if you have access to the Stieltjes transform as a function of some complex variable, and you take the limit as that complex variable approaches the real line, then the imaginary part of the result is exactly the spectral density. So there's this object, the Stieltjes transform, which is related to the spectral density by this integral, and it encodes the spectral density in its imaginary part. And this Stieltjes transform is quite useful, and I'll describe how it's useful in the next couple slides. So in the context of free probability theory, the Stieltjes transform is related to two additional auxiliary objects. And I will explain the utility of these very shortly. But the point of this slide, I just wanted you to take away that there is an object called the R transform and an object called the S transform, which are related to the Stieltjes transform by some functional equations. And the details are not so important, but the point is just you can perform some algebraic manipulations on the Stieltjes transform to get out this R and S transform. Okay, so the details aren't so important. But the utility of all of this is that if you have a random matrix A and a random matrix B, and you know their spectra, how can you compute the spectrum of the sum of the random matrix A plus B? And if A and B are what's known as freely independent, which I'll define in 1 second, then you can recover the sum, the spectrum of the sum, from the spectrum of the individual matrices using the R transform. And you do it sort of using this following, just kind of following your nose. So what you do is you have the spectrum of A and the spectrum of B. You compute that Stieltjes transform for each. Then from that, you use those functional equations from the previous slide to compute the R transforms. And then the magic takes place, because the R transform has the property that the sum of the R transform of A and the R transform of B is equal to the R transform of the sum. And then from that, you can extract again the Stieltjes transform, and then from its imaginary part, obtain the spectral density of the sum. So this is kind of magic, but it should be maybe familiar from commutative classical probability theory, where there's an analogous object which is just a characteristic function, or like the log of the Fourier transform. And that has exactly the same property in the commutative setting as the R transform does in the non-commutative setting. Okay, so the R transform is useful for computing the spectrum of a sum of random matrices. And the S transform analogously is useful for computing the spectrum of a product. Okay, so we have these great tools, but in red, I've highlighted this concept of free independence, which must be satisfied in order for us to use them. And so what does that mean exactly? So what is free independence? Free independence is basically, again, the non-commutative analog of classical independence. One definition of that is just that if x and y are random variables, such that the expectation of f of x and the expectation of g of y are both 0, then the expectation of f of x times g of y should be 0. And so this is one definition of classical independence. And free independence is just a kind of non-commutative extension of this. In particular, if you have some set of k, f, and kg, that for each of which the expectation vanishes, then the expectation of the product should vanish. Okay, so this is a little bit of an abstract definition of free independence, but it basically just means one slightly less formal definition, which I think is much more intuitive, is if x and y are classically independent, and they're matrices, and so if they're classically independent and their eigenspaces don't align in any special way, then free independence will hold. So that's the way I like to think about it, is that they're classically independent and their eigenspaces are also totally random with respect to one another. Okay, so basically just to summarize these tools, if we have some random matrices A and B, we can compute spectra of their sum and their product using the R and S transform. And that's exactly what we're going to do in a couple contexts going forward. Okay, so the first application of these tools is going to make use of the R transform. And it's in the context of studying the geometry of high-dimensional loss surfaces. So this is a bit of a change in gears. So let me try to just give some intuition for the kinds of questions I hope to answer here. So I'm going to be interested in critical points of the loss surface, also known as stationary points. They're places where the gradient vanishes. And critical points can be classified by the eigenvalues of the Hessian matrix at the critical point, basically the second order data about the function at the critical point. And okay, I should say as a caveat, here and going forward, I'm going to neglect the scenario where there may be 0 eigenvalues in the Hessian, in which case such classifications may require higher order derivatives. But for simplicity, let's just forget about that point for a second. And let's consider a single critical point in 2 dimensions. There's 3 options, basically. You could have a minimum, in which case both of the eigenvalues of the Hessian are positive. You could have a saddle point where one is positive and one is negative. Or you could have a maximum where they're both negative. And in the middle case, you have one negative eigenvalue, and correspondingly there's one direction of descent, one negative curvature direction. And the fraction of negative curvature directions is called the index of the critical point. So that's a concept that I'll be referring to going forward. The index of the critical point is the fraction of the number of negative eigenvalues. It tells you what are the fraction of the number of descent directions. How many ways can you go down? Okay, so this is for a single critical point in 2 dimensions, but obviously this is an incredibly simple model of a high-dimensional loss landscape. Just to try to bridge the gap a little bit before moving on, let me give some examples of multiple critical points. So suppose again you're in 2 dimensions, but you can see now if you have multiple critical points how the geometry of the landscape can look a lot different depending on how they're configured. So in the middle case, there's a global minimum, which is much lower in loss value or energy. I'll typically call the loss value the energy. There's a global minimum which has a much lower energy than the local minima, and also much lower energy than the saddle points. On the left side, you have a bunch of local minima. They're all about the same value of the loss. But the index 1 saddle points, the saddle points with one negative curvature direction lie in between the minima. They have much higher energy. And finally, on the right, you have all of the minima and the index 1 saddle points have about the same energy. So you could imagine, depending on which scenario you are in, optimization will proceed a lot differently, and you might want to adjust your algorithm accordingly. So it would be nice to know a priori which of these cases, or some others that I haven't listed here, you happen to be in when training your deep neural net. So let me briefly describe some things about what is already known regarding the geometry of high-dimensional loss landscapes. And in the context of neural networks with the general architectures, the answer is frustratingly little is actually known. What is known in specific contexts in answering very specific questions. So I think one of the most interesting recent results in this direction is in trying to answer the question as to whether all local minima are in fact global. And it turns out that for deep linear networks, this is in fact the case. And I think this is a highly surprising result. There's also a recent result from this year's ICML showing that it's almost true for nonlinear networks, so long as they have a particular kind of pyramidal structure. But when you start trying to ask more general questions, like what's the distribution of critical points? And I mean distribution with respect to the energy. So if you want to know how likely it is you'll find a critical point with a given index of a particular energy, that's what you would get if you knew the distribution of critical points. And if you try to ask this more general question, it turns out that the results are pretty sparse. There's some recent work by Anna Kormanska drawing a kind of analogy to spin glass systems in which they argue that there's sort of exponentially more critical points of high index. I think, and then there's also some work in the context of the field theory of Gaussian random functions, where they actually try to be a little bit more quantitative. And in fact, they're able to derive an explicit representation for how the index relates to the energy. So here, the index, again, the fraction of negative eigenvalues of the Hessian is alpha, and epsilon is the energy, or loss value, at the critical point. And epsilon c here is like the minimizer. So this says as you move away from the minimizer in energy, you happen to be at a critical point that has higher energy, you're more likely to have directions of descent, which I think is pretty intuitive. But it also says quantitatively how much more likely you are to have how many more directions of descent by virtue of specifying this 3/2 power. And I'm going to come back to that 3/2 scaling. Okay, so to describe the analysis that we did in this context, first I should establish a little bit of notation. So we're going to be considering a neural network parameterized by some collective set of variables theta. The global loss value, again, I'll call epsilon, or the energy. And previously I mentioned the Jacobian, the input-output Jacobian. Here I'm talking about the Jacobian with respect to the parameters. So this is a different Jacobian. It's the derivative of the output of the network with respect to its parameters. In terms of the Jacobian, the gradient is just equal to the error signal at the top of the network times that Jacobian. And then the Hessian, if you take another derivative of this gradient, generically decomposes into two pieces. The first piece comes from when you hit the error signal. So So you end up, through the chain rule, with another factor of the Jacobian. Basically, you have a Jacobian times its transpose. And that's kind of a generalized Gauss-Newton term, which I'm calling H0. And then the second term, when the second derivative hits the Jacobian, gives you a factor H1, which contains all of the second derivatives. This is just a very generic decomposition. Actually, it's not really necessary to talk about neural networks at all in this context. So the Hessian decomposes into H0 and H1. And let me just flesh that out a bit more. And now I'll specialize to the case of squared error. And in this context, H0 is exactly this J, the Jacobian J transpose J. And as such, it's positive semi-definite. It has no zero eigenvalues at all. And furthermore, there's at least no explicit dependence on the loss or the energy epsilon. There may be implicit dependence through how the parameters have been updated to get you to a place where there's that loss value, but it's not proportional to the loss explicitly. And secondly, this term H1 is proportional to the residuals. And if you take them to be normally distributed, that means the variance of this term contains the dependence on the loss, the epsilon, the energy. And furthermore, because H0 is positive semi-definite, this term is the source of all of the negative eigenvalues of H. So you can see where we're going here. We have this decomposition into two pieces, one of which is PSD, and the other of which contains all the negative eigenvalues and all the explicit dependence on the energy. So if we can understand how these two terms play off one another, we can understand how the energy and the index are related to one another. Okay, so with that goal in mind, we aim to make some simplifications by using some random matrix approximations. So in particular, as I alluded to a second ago, we're going to regard H as a structured random matrix. The structure is induced by the sum and also by the internal structure of H0 and H1. The internal structure in H0 is exactly the fact that it's product J transpose J. So the assumption we'll make here is that the elements of J are IID, random variables. And I think this is sort of the most, the simplest assumption we can make, which captures all the relevant structure of H0. And we'll further make two approximations on H1. We'll make an approximation that its elements are all IID, but symmetric, which is also known as a Wigner random matrix. And then we'll also specialize to the one hidden layer case with ReLU units. And without going into the details, I can just tell you that in that case, the random matrix distribution for H1 is slightly more complicated. It's what's known as a product Wishart matrix. But the details really aren't so relevant for this discussion. What is relevant is the additional assumption that H0 and H1 are freely independent. And if that's true, we take it to be the case, then we can compute the spectrum of the Hessian using the R transform. Because this is a sum of random matrices. Okay, so without going into too many details, let me just describe how that boils down. So the R transform of all of the matrices that I mentioned are known or can be derived fairly easily. For the Wishart matrix for H0, the matrix which is J transpose J, the R transform is just sigma over 1 minus sigma z phi, where sigma is some scale parameter we just set to 1. And phi is this crucial ratio that measures the number of parameters to the number of samples in the system. And in the two approximations for H1, we have two different R transforms. The details aren't so important, but they, as you can see, have explicit dependence on the loss, the energy epsilon. Okay, so without going through the details, basically we just turn the crank, extract the spectral density in the way I described earlier, and we do this for both of these approximation schemes. We can integrate that density from negative infinity to 0. That tells you how many negative eigenvalues you have. So this is the index. So we have an explicit representation for the index in both cases. And if we expand that for small values of the index, actually we find for both cases the same behavior, which is also the same behavior that was found by Bray and Dean in the context of the field theory of Gaussian random functions. So we find this 3/2 scaling as the energy of the loss moves away from the loss of the minimizer. We find that the index scales like the 3/2 power under this approximation. So this, I think, speaks to the question about whether the 3/2 power maybe is somehow universal, given that it's shown up in these several contexts. But given that we've made several approximations here using random matrices, I think it's important to try to verify whether these predictions hold in practice. So what we did in that direction is to actually simulate neural networks. And we use a kind of heuristic optimization scheme, which is attracted to saddle points. And we run a huge number of optimizations. And at the termination of each run, we found a critical point. And we measure the index of that critical point and its energy. And that gives us the scatter plot of points. And we have a different scatter plot for different values of phi, which is, again, is the ratio of parameters to samples. It tells you how over or under parameterized you are. And in the solid lines are best fit curves to this functional form, epsilon minus epsilon c to the 3/2, where epsilon c is basically the position of a minimizer. And you can see for small values of alpha, the fit is extremely good. And it's even better for for small values of phi. But it's still good for all values of phi if you zoom in close enough to alpha equals 0.
So just to make sure I understand, like we train like different networks for each phi.
Yeah, so in fact what I do, this is actually a memorization scenario where I have random Gaussian inputs and random Gaussian targets. And to change the value of phi, I just change the number of samples that I'm training against. Okay, so this is all I wanted to say about our analysis of the geometry of neural network loss surfaces. I see a question.
So if you use real data, not Gaussian generated data, will you again, do you have any measures of goodness of fit of the approximations that you did in the modeling?
Yeah, absolutely. I did look into using.
Can you just repeat that?
Of course, yeah. So the question was basically what happens if we use real data and not this Gaussian memorization task. And the answer I can give is it's slightly inconclusive to me at the moment. One of the issues with using real data is that it's hard to get a small enough data set for which one can compute the Hessian explicitly and run there's some 50,000 experiments summarized here. And if you try to downsample or something, a data set like MNIST, I think that induces some other kind of problems. So the short answer is it seems to be qualitatively similar, although the goodness of fit seems a bit worse. But that may be due to the fact that I just didn't run large enough networks to accommodate the type of data which I was looking at MNIST. Okay, I'm going to switch gears now and talk about another recent work. This is in collaboration with Sam Schoenholz at Google Brain and Surya Ganguly, who's here at Stanford and also at Google Brain, where we look at training very, very deep neural networks. And we've titled the paper Resurrecting the Sigmoid, basically because we find that sigmoidal units perform much better in this context than rectified linear units. Okay, so before diving into this topic, I'd like to make a potentially controversial distinction between what I'm calling very deep learning and deep learning. And so let me just say kind of arbitrarily that deep learning corresponds to neural nets with, say, fewer than 25 layers. What I mean by this is basically the depths for which training is feasible without using any really special tricks or architectural hacks, but which and may take quite a while, but it can be done relatively easily. And so the reason I say this is somewhat arbitrary threshold is that depends on the problem and all sorts of things. But I think you can enter a domain by considering networks of depth hundreds, 1,000, where those distinctions end up not really mattering, and traditional methods for training just don't work. And so you say, why do you care about very deep learning? Which I think is a great question. The answer is that it turns out in recent years, state-of-the-art methods in computer vision and object recognition, for example, are utilizing now networks of 100 or 1,000 plus layers. But they're actually not doing so without using some special architectural tricks. In the case of convolutional networks, it turns out to be very important to use residual connections or batch normalization, particular ways of modifying the architecture that allow training to progress. Other very deep networks occur in the context of recurrent neural networks, where you have long time horizons. And in those contexts, you can also see effective network depths of hundreds or thousands of layers. And also in those contexts, learning seems to be very challenging without using specific architectures, such as gated units like LSTMs. So one, I think, natural question here is whether these techniques like ResNet, batch norm, LSTM, etc., are reflecting any kind of important inductive bias, or whether they're just useful insofar as their ability to help us train these deep networks. And to look into this question, I think it's important to try to answer what's the intrinsic difficulty in training such deep networks? Like, where does the problem come from? And of course, this is an old question with lots of prior work. The main thinking on the topic relates, of course, to vanishing gradients and exploding gradients. But hopefully, with some insights from random matrix theory, we can say something new about this topic. So before digging into the details in random matrix theory, I should highlight some recent work by Ben Poole and Sam Schoenholz investigating necessary conditions for trainability. And I think these conditions are probably not very controversial and are fairly intuitive. But let me go through them in detail, because I think it's pretty useful. So the first necessary condition is just that the forward propagated signals don't vanish or explode. I mean, with depth, as you get to very deep networks. And I think even if for no other reason than numerical precision issues, this is a necessary condition. And just to hash that out a little bit more, here I've written down the layer-to-layer recurrence relation between the pre-activation neurons, what I'll call Z. And at initialization, we'll take the biases to be normally distributed with variance sigma b squared, the weights to be normally distributed with variance sigma w squared over n, where n here is the width of the network. And we're going to be considering the limit of large width. So we need this factor of 1 over n in the variance in order to ensure that the variance in the elements of Z is bounded in that limit. And furthermore, because we're considering this large width limit, the central limit theorem kicks in. And therefore, the distribution of the elements of Z is going to be Gaussian. It's going to have 0 mean, because B and W have 0 mean. And the variance is going to have some value, which potentially depends on depth. And the condition that the forward propagated signals don't vanish or explode in depth can be stated as a condition on the variance of that normal distribution. And in particular, the simplest possible scenario for it not to explode or vanish is that it approaches a fixed point. And empirically, that is what seems to occur. So the variance of the activation should approach a fixed point, which I'll call Q star. So this implies that independent of the layer, the pre-activations are distributed normally with variance Q star and mean 0. And one can ensure that there's no transient effects at small depth by normalizing the input to have 0 mean and variance Q star as well. So this ensures that the pre-activations all have the same distribution at initialization. And the existence of such a fixed point, it depends on the nonlinearity, whether you can do this, and the actual values of sigma w and sigma b. Just as an example, if you imagine taking a tanh network with the variance is less than 1 of sigma w, and the bias variance is 0, then you have this contractive mapping from layer to layer. And therefore, the variance will just decay to 0 in depth. But if the variance is bigger than 1, then the multiplication by w kind of expands, the application of f kind of contracts, and you can end up with a kind of balanced situation. Okay. Hopefully that condition was not too controversial. I think this one is not as well. And that is that the backpropagated signals should also not vanish or explode with depth. And we can just pursue a very similar analysis where we just write down the backpropagation recursion relation. At the top layer L, we can take the error signal equal epsilon. And then the error signals at lower layers can be obtained through this matrix multiplication by W and the nonlinear diagonal matrix F prime. So again, we can ask what happens to the variance. These, again, are normally distributed variables for the same central limit theorem reasoning. And we can compute the variance of, say, the first element. And the expression is as I've put here. Recalling that all of the z's, the pre-activations, are distributed the same way, independent of depth. Actually, this quantity, sigma w squared expectation of f prime squared, is also independent of depth. And we can call that function chi. It's a function of sigma w and sigma b because this fixed point variance q star depends on those parameters. But it's clear now, if you follow this recurrence all the way to the base level, that the variance of the backpropagated signal at the first layer scales like chi to the L, the depth. So if you want your gradients to neither explode nor vanish for large depth, you'd better have chi equals 1. Okay, so what this does, you have some transcendental equation, typically, separating the sigma w, sigma b plane into two phases. One phase has vanishing gradients. If you have sigma w, say, is too small. And in the other phase, you'll have exploding gradients if, say, sigma w is too large. But right on the boundary, you have this sweet spot where chi equals 1 and you have neither explosion nor vanishing of gradients. And this critical line was recognized in these prior works as being a great place to initialize, and found that you could train deep networks with this initialization, just choosing some point on this critical line. I should point out that all the points on the critical line are distinguished by the value of the fixed point variance of the pre-activations Q star. And this will be important later. Okay, so here I've described two necessary conditions for trainability. Now let me describe how we try to go beyond those conditions and see if there's any more conditions that could make for faster training. So let me try to recharacterize this condition on the gradients should not explode or vanish. Let me recharacterize it in terms of the Jacobian. So writing down the expression for delta 1, the backpropagated error signal all the way through the network, as it can be written as the error signal at the top of the network times the input-output Jacobian matrix, this dy dz. Right, just through the chain rule, if you just follow your nose, write down the derivative with respect to the input. You have the error signal times this Jacobian. And you can then ask, like, what is the expected norm squared of this error signal for various error signals epsilon? So what's the expected norm squared of delta 1 for random error signals coming in? And it turns out that the condition that chi equals 1, that gradients neither vanish nor explode, is equivalent to a condition on the singular values of the matrix J, namely that the mean squared singular value should equal 1. So this is like saying that on average, the backpropagated error signal through the network should have constant norm, on average. So this is what the condition means to have chi equals 1. It's sort of on average, the backpropagated error signals through the network have norm 1. But this also raises the question, what about the other singular values? Not just the second moment of the singular value distribution, but what about the whole distribution itself? Is that relevant? So the singular values of this input-output Jacobian matrix tell us how error signals can sort of stretch and skew as they move back through the network. And even if the mean squared singular value is 1, so on average, things look good, you can still have a large skew in the distribution with some large singular values and a lot of small ones, for example. And so in trying to understand the behavior of learning dynamics, we could try to analyze the full singular value distribution of this Jacobian and not just its mean squared singular value. And because J is a product of matrices, which we take to be random at initialization, we can use the technology I described earlier, in particular the S transform, to compute the full distribution of singular values of the Jacobian. And okay, I'm not going to go through the details of that calculation. I think it's maybe more informative if I just describe the results. And I'll do that with a kind of caricature. So this is what the Jacobian spectra look like for very large depth. So for Gaussian weights W and any activation function f, you end up in this ill-conditioned scenario where you have lots of small singular values and a few very large ones. The mean squared singular value is still 1, so on average the gradients are well behaved, but sometimes you're going to get a bad gradient because you'll touch one of these large singular vectors. If you try to fix the problem by using orthogonal weights, and you make the mistake of using rectified linear units, you will have the same problem. Your singular value distribution will also be skewed, become increasingly more skewed for larger depth. If you use a sigmoidal unit like tanh with orthogonal weights, but you put the weight variance to be too large, you take this value of q star to be too big, you'll also be in this same situation. But if you do things just right, you take orthogonal weights, sigmoidal activation function, and the weight variance to be close to 1, then you can get this sweet spot where the singular value distribution is well equilibrated and concentrates around 1, even for large depth. So this is, in a sense, a kind of prediction for what types of network configurations will train well and what types of network configurations won't for very large depth. Yes?
So it's true that Dunage allows you, if you have the weights, like good weights, to have like stable values, but like the range of the possible outputs is kind of limited when compared to like ReLU. And I wonder if it's not like limiting, like making the learning task harder by limiting like the range of values at each layer. And
well, absolutely. We're not saying anything about expressivity of tanh networks versus ReLU ones. Although I'm not sure I completely agree that tanh networks are less expressive for the reason you say. No, but I'm just talking about the feasibility of the learning task itself. And so we tried to see whether these predictions hold in practice. And so what I'm showing here is test accuracy, so generalization performance on CFAR 10 using networks of width 400, depth 200, so pretty deep networks, using a variety of optimizers. And in the colored lines show different initialization and activation function schemes. And you can see that if you use orthogonal initialization with tanh activation functions and sigma w close to 1, while also choosing sigma b such that you live on this critical line, you train much faster. And depending on how you measure it, if you make an accuracy cutoff of 0.3 or 0.4, this can be orders of magnitude faster. We also find that ReLU units don't seem to be sensitive to whether or not you choose Gaussian or orthogonal weights, and that they just train much slower regardless. And also, if the weight initialization is too big in the red curves, you see that the performance decreases significantly. So this is exactly in line with our theoretical predictions based on the distribution of singular values and seems to be borne out for these deep networks. So I should reiterate that this analysis really is only applying to very deep networks. So you all may have intuition that ReLU networks, for example, perform well. And I don't claim that that intuition is wrong. I just claim that you probably haven't been looking at depth 200 networks using ReLU. Okay. Given the time and the fact that I'm done discussing this paper, and I want to leave some time for questions, I think I'm going to skip this section. The paper is on the website if you'd like to read about it. Happy to discuss offline. But just to wrap up, hopefully I've convinced you to some extent that random matrix theory provides some powerful tools for studying deep learning. We demonstrated how to examine the geometry of high-dimensional loss landscapes using these tools, and also showed how to equilibrate the singular values of the end-to-end Jacobian matrix for faster training. So I think with that, I will stop. Thank you.
So I've collected some of the questions. Do you have some also? Maybe we could. So perhaps we could just begin with some of the things that students have asked in the discussion section. I'm not sure that I'm going to get. Several people asked the following type of question with different wording about the first half of the talk. And I think that would include you by, I'm not sure I can pronounce this correctly, Engeron Marie Eve Nicolas something or other that was truncated. Silu Tang and Zi Yin, all of them asked variations on the question that in your paper you talk about, this is the first part of the talk, you talk about basically a single layer is at the core of your analysis. But given that people really work on things with a lot more depth, what do you see as the generalizability of your analysis to a true deep layer network, and what would be the technical challenges to achieve that generalization?
Yeah, absolutely. I think trying to understand how to apply the techniques of studying the geometry of multi-layer neural network loss surfaces is a good one. I should say that that in our work we look at two approximation paradigms, one of which is sort of meant to be generic and apply to arbitrary network configurations, where we neglect the internal structure of this H1 matrix and just approximate it generically as a Wigner random matrix. And I think that approximation can capture some of the high-level structure that we expect for deep networks, or for any neural net, generically speaking. The second approximation, we did focus on single hidden layer ReLU networks and had a more sophisticated analysis, which hopefully gave more precise predictions. In trying to generalize that more sophisticated analysis to multi-layer networks, there are definitely a host of challenges, and most of them are related to trying to solve aspects to try to derive spectra of random matrices with nonlinear dependencies between the elements. And actually it was this question that motivated some of my follow-up work in trying to study nonlinear random matrix theory, which unfortunately I didn't chat about today. But I think really developing those tools a bit further will be necessary in order to do justice to that analysis.
So, Jeffrey, our course has been recently on Hacker News, and there has been a lot of, interest in this. And so there are a lot of discussions on Hacker News about Stats 385. So I was hoping that maybe you could answer to one of these questions that somebody is asking. So somebody is saying, why is the lack of theory a problem? At some point, we have to accept some problems are out of our league and use whatever is available, even without fully understanding it. We can't even understand simple specializations in computer vision, yet we expect to understand a more general method. It is not like 15 years ago. There weren't math theorems proven by enumerating them on a computer. I understand it breaks psyche and pride of some scientists. So what? Universe can't be expected to fit into humanity's collective brain. So do you have a response for bit L?
Gosh. Okay, well, I'll try to be somewhat serious, I guess. Machine learning and deep learning models are deployed in lots of products that affect human lives on a daily basis. And whether you're talking about self-driving cars, potentially, or more mundane things like giving you accurate directions on the road or whatever, it's important to understand failure modes of those models when they're interacting directly with people's lives. And if you have no theoretical understanding of the model, how can you provide those failure guarantees? So I think that's really the most important practical reason. But also from another perspective, the history of science, I think, dictates that there's an interplay between experimental observations and theoretical predictions. And you can't expect to really pursue one without the other.
Okay, some more questions that students have posted.
I just want to say that this was a great answer.
Okay.
Great answer.
So off mic, Emmanuel Condez commented that Jeffrey's answer was a great answer. So several more questions were expressing common interests. So I think Boan Dang asked, the networks that people are actually interested in are convolutional, and in that structure you have weight sharing, which is somewhat different than the random matrices that are being studied in this paper. How do you expect the conclusions to be affected by that?
Well, that's a fantastic question, and one that we're actively pursuing. The short answer is that indeed the analysis must change because of that weight sharing. The precise conclusions, I think we still haven't quite reached. In particular, how to analyze the Jacobians and the spectra of those Jacobians in those cases is still a question we haven't quite nailed down. But I have to completely agree that that's a very important next step of making this work practically relevant.
Philip Kenka Huang and Brian Young both had a question about how your analysis of training speed might be adapted to teach us something about generalizability. Is there anything in the singular values that can teach us about which networks will generalize?
I think generically speaking, if the network is very sensitive to perturbations in the input space, that it's likely to make very strong deviations from what you might hope when it sees new data. That is just to say, if there's some large and some very small singular values, then when we show some test data that you've never seen before, I think there's a good chance that you're going to overlap with one of those strong singular directions and push your predictions well outside of the good regime. So, I mean, I think from a hand-waving perspective, that argument suggests that having a well-equilibrated Jacobian will be useful for generalization. But saying things more quantitative than that, especially when you take into account the dynamics of training and whatnot, I think is really an interesting question, but unfortunately, really beyond my capabilities, at least, at this current time.
So Ditya Grover had a question about why the R transform with ReLUs is different than somehow a general analysis of R transforms. And maybe that matches my question. What is it about ReLUs versus Tanch that really is the secret sauce in your result? Is there some simple hidden little element that you could explain there?
So let me try to answer that question from two perspectives. I'm not sure if the question was referring to R transforms or S transforms, but let me assume it was referring to R transforms and discuss for a second the first part of the talk, where the analysis we conducted for single hidden layer ReLU units was possible basically just because of the fact that ReLU is very simple. It's basically linear or zero, which means that a lot of the computation of the spectrum is technically feasible and easy. So that's why we pursued ReLU in that context, and I'm not sure how the results would change if we were able to do the computation for Tanch. But to address your question, and to address the other question, assuming it maybe meant S transform, with regard to the second half of the talk, the secret sauce is the fact that the activation function is linear about the origin. When you decrease sigma w, the weight variance, closer to 1, you push the fixed point pre-activation variance q star close to 0, which means that the input to the nonlinearity is close to focused around 0, which means that you care about the behavior of the activation function in that regime. And Tanch and other sigmoidal units are typically linear about the origin. And we're basically exploiting the fact that we're near linearity to derive these results.
Okay, thank you.
So maybe you would open to the audience. So if you have questions for Jeffrey, do you have a question?
Thanks for the nice talk. I'm just wondering, if you use batch normalization, then how would you compare the trainability of TANH and ReLU activations?
This is a good question, and maybe we should have tried to include some plots to that effect. And the short answer is, I'm not 100% sure how training time compares if you consider batch normalized networks with these well-equilibrated non-batch norm networks. So the short answer is I don't know yet. But from a theoretical perspective, we have thought a bit about batch normalization, and it seems quite challenging to extend our results in that direction. I'm not sure it's impossible, but part of the reason we're able to do this analysis is because we can utilize the central limit theorem. And when you include batch normalization, the distribution of elements in your hidden layer ends up depending on other elements in the batch in a complicated way. And maybe it's possible to finish that analysis. We haven't given it a full, rigorous attempt yet, but we don't really quite know, I guess.
So this sort of in the same direction, Yiguang was asking whether is there any network regularization techniques such as dropout that you believe would rather reduce the correlations in weight when you're training. So, explicit regularization techniques, have you tried to see like how they affect this spectrum?
In a nice paper by Sam Schoenholtz, Deep Information Propagation, he analyzes they analyze the forward and backward propagation of signals, basically the necessary conditions for trainability in the case of dropout networks. And they find that including dropout actually prevents the existence of this fixed point norm Q star. So in some ways, it really makes it impossible to train very deep. And I think also impossible to train arbitrarily deep networks unless you reduce the dropout fraction to a very small level.
So I know this already because we had an interview that will appear in the highlights. But I'm gathering from what you've just said that your opinion of dropout is less than enthusiastic.
I think dropout has had enormous empirical success, so I don't want to badmouth it too much. It just is annoying from a theoretical perspective. Let me just put it that way.
Any other question from the audience? Back there.
Yeah, so to get the trainability, you said you kind of need to be in this critical regime where nothing's like, blowing up or vanishing. I was just wondering about what that says about, can you say anything about like the expressivity of the network in that regime? Like, is that, because the expressivity is related to all these Jacobians and things like that. Is the expressivity separate from that? Like, can you have, like compute like highly curved functions even though you're in this critical regime for the training?
Yeah, actually there's a very nice paper by Ben Poole examining basically exactly that question. In the phase diagram I put up before, let me see if I can pull it up. I had, in addition to the vanishing and exploding gradients label, an ordered and chaotic label for the two phases. And that, I think, corresponds exactly to the answer to your question. If you move away from the critical regime in the direction of too large of a sigma w, you end up in this chaotic behavior where space kind of expands and contracts really kind of chaotically, and you have this really high curvature, and the functions are poorly behaved. And on the other side, it's ordered. You get in this bias-dominated regime where the effect of the weights kind of diminishes, and you have correlations induced solely by the existence of the bias vectors basically at each layer. And so yeah, there's something special about expressivity right on this critical line because you're hovering the boundary between these two phases.
I also want to ask Mona's question because I thought it's very interesting. In your paper, Geometry of Neural Nets, Lost Surfaces via Random Matrix Theory, you have studied the phase transition and the number of negative eigenvalues of the Hessian matrix in terms of the error of the residual. Let's say we are above this threshold. Does this mean that with high probability, the Hessian matrix has negative eigenvalues, and so we are in a saddle point instead of a global minima?
Yeah, so that's a fantastic question. Basically, just to rephrase, if we have a value of epsilon, which is above the point where these curves intersect the x-axis, then the question is, do we expect with high probability to have lots of negative curvature directions? And to answer that question, the answer to the question is probably not as far as I have evidence, because what I'm reporting here is the mean value of alpha across a large number of runs. So I don't really have much information or intuition about the actual distribution, but I can say from prior work, for example, Anna Koromanska et al. Have argued that this is in fact the case, that it is with high probability that you have lots of descent directions. But that was in the context of spin glass systems, so I'm not 100% sure how that carries over.
So some other students were interested in the question of, since you're talking about deep networks, and the dogma of deep networks says that you have to use skip connections. What do you have to say about skip connections? Can your analysis deal with skip connections, or how would it ultimately have to change to cope with that?
Yeah, absolutely. So our analysis can definitely deal with skip connections fairly easily. And the reason we haven't pursued this analysis in depth is because, as far as I'm aware at least, there have not been really successful deployments of networks with only skip connections and not batch normalization. It seems like these ResNet architectures that are successful always utilize both. And somehow utilizing both, I mean, they interplay off of one another, I think, in an interesting way. And since we haven't quite yet figured out how to attack batch norm, we haven't attacked ResNets, and therefore haven't thought too hard about skip connections. But it can be done, and I'm not quite sure what the results would be, though.
You have a question? Any other question?
Some other students were interested in how does real data on actual CNNs compare, like, is there some way you can look at a data from a CNN and see if your theory is going to be applicable?
So we have some preliminary work studying convolutional networks. We haven't finished yet the analysis of the Jacobian and its spectrum, as I mentioned before. But it does seem like on real data with convolutional networks, using some of these tools actually can produce basically vanilla CNNs that can be trained up to maybe 1,500 layers. So I think in a roundabout way to answer that question, I think sort of the proof is in the pudding. It does seem to enable training of very, very deep CNNs, and I think that's what we ultimately care about.
So Jeffrey, RNNs are very hard to train. So do you have any experience training RNNs with your method of initialization, and see what's the effect of that?
So we have some very preliminary results in this direction, which suggest that, at least on certain tasks, we find, let me be conservative and say, an order of magnitude speed up in training time by using these types of equilibration techniques relative to standard init schemes. So yes, it does seem to work.
Sure, it does. Questions? Objections?
One of the response there is about RNN, that your equilibration technique would help. But I want to follow up on that, since you are not enthusiastic about using dropout for very deep net. In some sense, RNN can be viewed as very long, repetitive, deep net, right? And dropout indeed doesn't work well there. You need to do tide weight dropout on RNN. Do you have any explanation on that?
I don't have a concrete mathematical explanation, but I think the intuition you alluded to maybe holds. And the same reason that maybe dropout doesn't work in very deep feed-forward nets is probably related to how it potentially fails in the recurrent setting. I should say that I think I should qualify my previous answer by saying we have not looked in depth at gated recurrent networks. My comment about this speed up in training was for vanilla RNNs. And in the vanilla RNN case, at least, for ReLU units, that has a kind of similar behavior to the feed-forward case with ReLU networks. And I think people have, in practice, found that training RNNs over long time horizons with ReLU activation functions is very challenging. And I think the reason for that is closely tied to how the singular values become very poorly conditioned.
Yeah, so I actually want to maybe finish by reading one of the things. Okay, so on Hacker News, also that wasn't the only comment. There are many comments you can go see about Stats 385. It's a huge selection of comments that you have. But one of them said, "What a privilege to study at that college." So I think you're all privileged to be here. Okay, well let's thank this speaker and yeah.